Okay, so this is a different type of thing. It is slightly related. So basically, this is a piece of work we're doing which involves a process modelling approach, which I'll explain what that is. And we're looking at figuring out what our diagnostic capacity is so we can make better decisions. And I'll focus this in reference to vaccination. So in New Zealand, we have a diagnostic surveillance strategy. We've been working on this for quite a while, and it's pretty much ready to go now. It's basically designed to improve our efficiency and accuracy of diagnosis for foot and mouth disease. And we have plans for the eradication phase and also the proof of freedom phase. So in New Zealand, we're actually going to use diagnostic testing as our main clinical diagnosis rather than clinical sign examination. So the key features are that we have made the decision-making for all the sampling and for all the testing algorithms we've done are predetermined already. So for at the farm level and for at the laboratory level, it's all set up and ready to go. With the eradication phase, we've got targeted diagnostics. We're looking particularly at enhancing our preclinical diagnosis. So we're focusing on the area there where virus is present before clinical signs become apparent. We want to delimit our outbreak faster. We want to get these animals before they become clinical, improve our management, reduce our spread of infection, reduce the outbreak overall, and we want to avoid having to do preemptive culling. So we're going to be using diagnostics before we do any culling. For the proof of freedom phase, the sample numbers and the testing algorithms are pre-validated, and they have the statistical confidence necessary for a claim of freedom based on the testing we'll be doing. So for the eradication phase, basically the main sort of points of it are that we have a property risk categorisation and priority setting determined by the planning team ahead of time before we send any vets out to the field. So you won't be able to see it there. This is the submission form that we've got in electronic format. So basically the risk categorisation is breaking them down into whether they're at-risk properties or report cases or protection zone surveillance around the area. Within the at-risk properties, which is obviously the contiguous properties, the movement traces and the airborne spread, we also have a time factor as well. So we have it broken down into 3 exposure times of when they were likely to be exposed. In New Zealand, we have a movement database and we've got some really good tracing tools, so we should actually be able to understand when we think these animals were exposed. The foot and mouth submission form is integrated into LIMS already, so we can take all the data straight from these submission forms into our laboratory information management system. It's electronic. We're going to have a front page app which we're developing now that will go out with the patrol vets into the field, so all this information will come straight into us. Our samples will be barcoded and the whole thing will be all brought in together, and then this information can feed back into the intelligence and planning teams as well. So the foot and mouth submission form that goes out with the patrol vets actually guides them as to what samples they're going to be taking, and it tells them, it basically just records whether the clinical signs are absent or present on that farm. If clinical signs are present, then that changes how we're going to test, because we're suddenly going to start looking at serology because the clinical signs will supersede that risk categorisation we came up with previously. And then when the samples arrive at the lab with this form, in its electronic version, it also tells the laboratory how they're going to test these samples. So we have 1 of 3 testing streams, which will be highlighted on this form, come to the laboratory and they go through that particular testing stream. So basically, these are serology as a priority and antigen detection as a priority, and then if we get negative results, they swap over and go down the other stream to make sure that we didn't just get our timings wrong. So basically what we're doing is we're targeting our testing per property for how likely we think that property is to either have antigen or antibody. And that should reduce the amount of testing we have to do because we're targeting it. Okay, and then the proof of freedom phase is, obviously more based, it's serologically based. We have a follow-up system as well. It's based on the OA guidelines, so we've worked out with our tests and our test sensitivities and specificities what sample numbers we need to get the confidence we need in these test results. And we've got a DEVA testing algorithm as well, which we'd use for vaccinated animals. Okay, so the laboratory capacity modelling, which is what I'm going to talk about, is basically it's a combination of this process modelling and outbreak scenario modelling as well. So process simulation means that we take these individual steps of the testing parameters, so the testing algorithms, break them down into steps, and for each of those steps we can attribute resources to them. We can attribute time, staffing, personnel, well, that's staffing. And then we can just look through every single one and formulate what our capacities are. So if we just look at the SP ELISA test, just to get to that box and sort of do that one test, we're looking at all the steps involved with bringing the samples into sample reception, the processing of those, getting them to PC3, getting them into the actual ELISA test itself, and then if you can see there, we've sort of broken down the ELISA test into about 12 steps. So we can define even the movement, like how long it takes to get from one of these steps into the next within the laboratory. So everything's broken down. If we go to the next slide, you can see there that this is one of the models here. So we've got some different tests. We've got our samples coming in and moving through the different processes. We run these with how many inputted samples we think we're going to have. We adjust our resources and our settings with these, and then we can come out with nice graphical outputs that tell us things about the model, basically. So the things we can see from this when we look at the outputs are whereabouts the samples are held up, how many samples we're actually getting through the system. We can see like backlogs where samples aren't coming through. We can see what sort of resources we need to change to make this work better and to improve our efficiency. We can run it as an unconstrained model and just see what happens and see what it shows us of like what sort of areas we could really improve on resources. And then we can run it constrained where we say, well, we've only got 20 cabinets, so we're going to use 20 cabinets, and then look at what sort of areas it sort of highlights as being restrictions for us. So it's quite a useful tool to be able to go through and see, and we can change every part of this. So the objectives basically are that we want to understand our capacity, and that's the main point of this, is that we've got a laboratory. We want to know basically how many tests are we going to get out of this laboratory in a day. So what we want to do with this model is we identify the significant constraints and bottlenecks within the testing processes by changing our things and having a look around. We want to see the resources, how much staffing, how many resources we need to overcome these, to improve our efficiency, to get as many samples tested as we can. Another part of it is to analyse and make a business case for getting some more high throughput machinery to see if it will actually significantly improve our capacity or not. And the main outcome is, with our realistic resourcing, what we actually think we can achieve, the people we think we can get into the lab, the equipment we think we can get, how many samples will we be able to test every day with our testing algorithms, the way we've got them set up. And the other thing is to understand the demand. So this is where the EP modelling comes in. So we're using Interspread Plus and estimating the number of samples that should be submitted to the laboratory every day. So what we want to happen is that the number of samples we have coming in are actually going to be met by the capacity of the laboratory. We don't want a whole bunch of samples coming in and then the whole system will fall over because there's not that capacity to test them. So how we're going to do that is to I'll get onto that. So the proportion of these also with the testing algorithm arms, so we've got the serology versus the antigen detection as well. So we want to estimate how many are going to be going to those streams because we want to accurately see which of these ones we're going to be testing for. We also want to look at the positive and negative rates, true or false, because we're going to be looking at all the complete demand. So if there are samples that need to be tested through different algorithms, confirmation testing, we need to add these in as well. So the main aim for the eradication phase is, which is the last step actually, this is once we've done this prioritisation setting, we've finished with our setup for our surveillance program. So we want to develop a prioritisation system that will align the inputted samples with the capacity to test them. It's basically necessary so that this all works. We need an effective prioritisation system that allows for the most important properties for the control of the epidemic to be tested first. The other property, if it's a large epidemic and we do have more samples that we can't test, then those properties would be going on back onto the clinical surveillance like they would have under the old system. It would be useful also to define trigger points, like number of IPs, where we actually stand up these prioritisation systems and then step them back down again and start taking all samples again. And for proof of freedom, basically what we want to do is answer these questions. So we've got our estimates for our testing demand, we've got our estimates for our laboratory capacity, so how long will our proof of freedom take us under normal settings? So this is going to be a big question for us, and this is what we're just starting to work on now. Can we achieve it within the 3-month stand down? Is it possible for us to actually do this? We're going to identify the trigger points where we might outsource our proof of freedom testing to regional laboratories, and we'll also have to look at what their capacity is as well, so we can factor that in too. And if the OE did change their policy to allowing zonification within a country, would we be able to test for proof of freedom as well as outbreak control at the same time? Would we have that capacity? Vaccination and DIVA testing. So basically using, we're using the scenario modelling of with vaccination compared to without. So similar to the last talk, we can use the scenarios that they've developed in there and actually apply them to see with the capacity modelling what our estimate for our additional demand would be. So how many more tests are we going to have to do if we do this DIVA testing as well? If Vaccinate to Live is adopted, will it extend the time beyond the 6-month minimum that we have to stand down before we can make a claim for freedom? So basically we have to do all our proof of freedom, then we'd have to do DIVA testing as well. If the OA policy is reduced to 3 months, will we be able to meet that deadline? Will it make any difference to us? Are we going to be able to do our proof of freedom and our DIVA testing within 3 months? And the other factor to consider against these, because obviously this is going to come up with, it's going to take longer, there's going to be more samples. And in the last scenarios where I was just talking about the vaccination, it was the mean vaccinated animals for those outbreaks was 1.5 million. So if we had to test all 1.5 million over 6 months, it works out to be 8.5 samples a day, testing every day for 6 months. So that's just the DIVA testing. That's not the proof of freedom as well. So that's a lot of testing. Cool. So we know it's going to be more, but would the additional DIVA testing time be offset by reducing the size of the outbreak and therefore reducing the outbreak testing requirement? So that's something we can look at doing the modelling to see if the payoff of reducing the outbreak will make up for this extra testing that we're going to have to be doing. And this is the last slide. So basically, it's really important for informed policy decisions on vaccination. So knowing what our capacity is, how well our laboratory can actually support a Vaccinate to Live policy is really important. It obviously needs to be considered alongside everything else that's related to vaccination. But basically the implication is that it could extend our Vaccinate to Live policy, could extend our return to freedom time considerably. And then we have to weigh up whether that wait to return to trade and the economic losses from that are worth the vaccination. And the worst case scenario would be that we don't have this information, we can't provide it to our policymakers, a Vaccinate to Live decision is made, and then we realise we can't actually support the testing, and then we have the decision of can we manage this extended time until return to freedom, or do we have to return to Vaccinate to die, and all the implications that would go with that. Thank you.
Thank you very much, Kaidi. That was a fascinating talk. We've time for one short question, if there's any. I see a question at the back from Melissa there. Nadia, please.
That's really nice work. I guess my question relates to, does the throughput model take into consideration normal business operations of the laboratory, or is it assuming that 100% of both the personnel as well as equipment resources are being dedicated to outbreak response? And does that change depending on what phase of the outbreak you're in, whether you're still trying to control the disease versus trying to demonstrate proof of freedom?
At the moment, we can change all those factors. It's very easy for us to do that. But at the moment, if we've only got one high containment laboratory in New Zealand, so it would be totally dedicated to foot and mouth disease during an outbreak. When it got into proof of freedom phase, that might be a bit different. But we can change those resources. But we'd pretty much be assuming at least the first few weeks, we'd be pulling everyone in to do the testing. Yeah.
Great. Thank you again, Katie.
Thank you.